I will want to announce Stefan Hardy. He will speak about next best actions using continuous intelligence. Continuous intelligence through closed-loop machine learning can be used to efficiently solve many next best action businesses problems. We will describe a reusable pattern for activating internal company data for next best action decision that continually updates its model and can track changing customer preferences. We will illustrate also this with a real-world use case in the insurance industry. Stefan is a data scientist and thought leader and CEO at Ambiata, and a specialist data science services provider based in Australia. He has delivered major data analysis and is an inventor of 20 US patents and has more than 20 academic publications. Welcome, Stefan.
Thank you. My name is Dr. Stephen Hardy. I'm the CEO at Ambiata, a Sydney-based data science company. And I'm going to talk about next best actions using continuous intelligence. So a next best action is something you can do for your customers. And we've broken them down into 4 different areas: engagement, satisfaction, conversion, and behavioral. And what we're going to talk about today is a use case in conversion, that is quote customization. Customizing a quote, personalizing it for an individual customer to help improve an outcome you're trying to drive in a business. And we're going to do this quote customization using continuous intelligence and contrast it against usual batch machine learning to show how these new systems work. We'll do this through a case study where we're going to look at setting the defaults on an insurance quote. And here's a mock-up of the home insurance quote page. This is what we're going to personalize based on what we know about the customer. Lots of things we can personalize. Here we'll talk about the promoted payment term, yearly, monthly, or fortnightly, the channel which can be bought through, and also the amount of excess initially set. So what we want to do is personalize this using machine learning. So this is an example of an automated decisioning system. And when you're building automated decisioning systems, you really need to think about the ethics of what you're doing, in particular AI ethics. So this is the list of the Australian government's AI ethics principles. And we always start here when it comes to understanding if we should be doing a particular type of next best action recommendation system, rather than whether or not we could do it. I won't go into any detail here, but for the use case we've got, the ethical considerations are largely mitigated by the fact that the end user can override every default that we set for them. But there's still things you need to think about. Another thing you need to think about up front is, what are you optimizing for? The business may have different requirements. Here we've got a couple of different things. We've got conversion, that's very much a short-term outcome, but then value and customer satisfaction, which are 2 longer-term outcomes. Really, if you're doing something closed loop, then having an immediate response is useful, but you can change these algorithms to allow them to take into account longer-term response as well. The third question you need to think about upfront is whether or not it's worth personalizing at all. And there are 2 things that you need to think about here. The first one is, if there is a business as usual action, sort of a default action, does it leave some of the customers dissatisfied? If not, then you may as well just keep using it. If there is a group of dissatisfied customers, the second thing you have to ask is, do you have data that will be predictive of their preference? Now, sometimes you can't know until you try, but if you don't have any data that's predictive of their preference, then there's no point in trying to personalize. Right, so for our home insurance quote. We're running this on a digital service that collects some data about the person, i.e. where they live and that sort of thing. We want to merge that with internal data to make the best prediction as possible. Now, how that works is that the digital service collects some data, sends it to our algorithm, which enriches it with internal data. The quote is then set and shown to the person, and the digital service then reports success or failure. Now, I'm going to build this out as we go, but the first question we've got to ask is, what sort of data do we have and how do we process it? Now, in this case, we're really only looking at incorporating structured data into our predictions. We've got the quote data, some customer information, historical transactions, and some third-party data. But it's also possible to include unstructured data into these systems, and I'll talk about that a little bit later. Now, to access this internal data, the digital service has to call two APIs that we set up. The first is a prediction API, and the second is the outcome API. Now, the prediction API uses internal data to enrich the features of the query to make better predictions. And it gets that data from internal data stores, having gone through the appropriate data governance process. And that gets added on to the online data. Now, accessing internal data is often quite complicated, and we wanted a system that we could deploy into many people's different architectures. So we built something on top of Kubernetes, which means that we can deploy into all the major clouds, but also into some on-prem systems as well. Now, internal data services typically aren't performant enough to do real-time decisioning. So we have a real-time data store that essentially keeps the data that's required for real-time response. It also saves all the outputs of the system, such as the features we use for machine learning and the outcomes we get across the outcome API, so that we can learn from that in real time. Now, if we add a machine learning system, we'll have essentially the simplest possible solution to this next best action recommendation, where the digital service requests some default from the prediction API, which can reach out to the batch inference API to get a prediction, return it to the digital service, which presents the quote and reports the result. So that's as simple as it gets. But the question is, where does this batch inference API, this form of machine learning, get its data? Now, I assume most of you understand this, but just to be so we're on the same page, machine learning typically takes 3 stages. You collect some training data where you'd want an example of the outcomes for every action that you might give. You'd build a model to predict the best outcome for each customer, and then you'd run that model in production. Now, in our case, there are only examples of the business as usual action in the historical data, which was yearly payment for this insurance quote. So what do you do in that case? You don't have the training data for the other options. Well, typically in a batch learning model, what you'll do is you'll take some business rules and apply a random action to a certain fraction of your customers. So for those random actions, you'll have your quote data, your customer info, your historical transactions, your third-party spatial data, all as features. You'll have your suggested action and an outcome. And you can learn from that in a batch learning model. Now, if you think about this algorithm, at the moment of this architecture, you've got 2 methods of generating next best actions, machine learning or business rules. So what we do is we actually have a configuration system that lets you route traffic either to the business rules or machine learning to select and specify which method of action is going to be used to make predictions for each request. Now, as I said, there are 2 models here. We've got batch learning, which I've talked about, but then continuous intelligence, which is actually the subject of this talk. So batch learning, you take historical data, you construct some features, you build a model, you validate that model, and you deploy it. At that point, you're essentially collecting outcomes and checking how well your model's working. And as the model drifts, as it will because customer behaviors change, you'll have to rebuild that model, revalidate it, and redeploy it. And typically that happens on sort of a weekly or monthly time frame, depending on your traffic. The continuous intelligence algorithms are different, and they solve this cold start problem differently. You construct features, you deploy your model not knowing anything about how your customers respond. You make some predictions, which are by their nature uncertain. You collect some outcomes, and you update your model immediately. And you run that in a loop, continuously improving your model. And throughout, you monitor outcomes. Now, batch learning, typically what you do when you have, say, 3 actions, you'll make a prediction for each action, what the outcome is going to be, and you'll select the action with the greatest predicted reward. In this case, you'd be selecting action 2. Here's another example where the greatest reward would be action 1, and you'd select that one. Now, in the sorts of continuous intelligence algorithms that we use, they're known as Thompson sampling contextual bandits, and you can look those up. You do something slightly different. These continuous intelligence algorithms model the uncertainties of their predictions, which means that when you're selecting actions, you can select actions not according to whether or not you think one is going to be the biggest, but whether or not there is some chance that is going to have the best reward. And you select the action according to the probability that it's going to be best. So in this case, where the uncertainties of action 1 and action 2 in terms of their predicted rewards overlap, there's actually a chance you could select either, but there's no way you would select action 3. Now, the other part of these algorithms is that they update their probabilities for every observation. So what's happening here is you're exploring the space of possible best rewards at the same time as exploiting what you know so far. Now, there are some advantages to these sorts of approaches. Now, this is a plot of reward over time with 4 different periods. Now, for a batch model, initially you know nothing. So you collect some training data and your outcome is not great because you're basically doing random selection. Then you train a model and the reward you collect is good, but it will slowly tail off as the environment changes. You retrain it once you hit some retraining threshold, and perhaps there's another change in the environment that makes things, the model worse more quickly, and you retrain again, and so on. In terms of these continuous intelligence algorithms, what happens is you get much better behavior at the start because you learn efficiently, and it's more adaptive to market changes, so you don't have to wait for a threshold to be hit before you retrain. So this is the continuous learning part here. There's also another advantage, which is what happens when you introduce a new action. In the batch learning model, you basically have to start throwing random actions at people again. So you have to reset your training data to include the new action. However, in a continuous intelligence algorithm, because you're basically building a model that has uncertainty built in, when you introduce a new action, that model is very uncertain about that. So there is always a chance that that action might be the best. So these algorithms will naturally choose this action 4 to experiment on due to that uncertainty. This is a very efficient way of learning and gives you much more flexibility in the sorts of actions you might deploy in a next best action scenario. Now, I talked a little bit before about how you actually do batch learning in a pattern. You create your model based on historically corrected data. You deploy it into some ML ops framework. You watch for drift, and at the same time, you might improve the model either by introducing more features or just through more training data. And then you go around that loop. Continuous intelligence is different from that in a quite subtle way. As I said before, you just create your model and you put it in production and it learns. That's great. But due to this experimentation process, sometimes it will select actions that are quite unlikely. And if you use just your usual batch machine learning methodologies for building new models based on that data, that can introduce some distortions because it overweights these quite unusual or random or rare events. So you have to use something called off-policy evaluation, which is a method of reinforcement learning for evaluating how good different policies of sequential decision-making algorithms are. And to do that, you have to store the propensities that you use to select each action. So rather than just having features and actions and outcomes, you have to store features, actions, outcomes, and propensities, and then do off-policy evaluation to improve your models. So that's a significant but subtle difference in these continuous intelligence algorithms. Now, you've probably already interacted with these algorithms. For example, Netflix uses these algorithms all over the place. There's a blog article on this, very interesting reading. And most of the other major digital properties are also using these algorithms in different ways. I mentioned before about using unstructured data in these algorithms. Essentially, if you want to use images, audio, emails, or calls, you can do so, but you need to convert this data into embeddings, that is, lists of numbers using deep learning, and then they can be incorporated into these contextual bandit framework. So we've really started to build out our architecture here. Here we now have 3 different options. We can run business rules, batch inference, or continuous learning. But how do you actually run these things in production? Now, it turns out to do continuous learning, you need a rock-solid MLOps framework. What we use is something called Selden Core, which is a great open source framework for deploying machine learning models. And it runs on top of Kubernetes, so it's platform agnostic. It supports all of the sorts of machine learning models we want to deploy into production, and we've implemented our continuous intelligence algorithms as Selden Core graphs. So once you've got this running, the last thing that you need to do is to be able to compare different algorithms to work out what works. Right? And to do that, we run experiments. Because we can route different traffic to different algorithms through our API, we can compare, say, an XGBoost model to a bandit algorithm or 2 XGBoost models. And what that means is that we can make scientifically valid measurements of which algorithms work best in production. And for our quote flow model, we showed that our continuous intelligence algorithm outperformed a periodically retrained XGBoost model. Finally, what you need to do is measure the outcomes of what you're doing to make sure that you are treating your customers fairly, that you can explain the outputs of what you're doing, and that you know how well it's working in production. So we have a custom UI for looking at experimentation output, and it also measures biases with respect to different actions. We also rely on the MLOps framework to give us outputs in terms of the observability around how the models are running in production in terms of response times and training and outcome accuracy. And we have observability through Splunk, so we can check what's happening for any decision that's made by the system. So in terms of the architecture I've drawn out here, the digital service calls the client API. That API enriches the call with internal data, and that call is then routed to either business rules or machine learning by the configuration system, All of the data that is collected is stored, and both the MLOps framework and that store are used to measure the outcomes with respect to customers. And here's the full detail on that architecture. Now, I'll just summarize what I've talked about here. We built a next best action personalization system using continuous intelligence. It's set up in a way that we can run experiments so that we can understand what works best in production. And we've seen really great outcomes from these continuous intelligence algorithms. For our use case that we've illustrated here in terms of home insurance quotes, we had a 15% uptick with respect to the business as usual actions. It's all underpinned by a great MLOps framework, which is really important to keep essentially the systems running, but also to understand what's going on so that you're treating your customers well and fairly. And that really means that we can support AI and data ethics in our systems in production.